So this is a fun little application of Taylor series. So we're going to talk about Euler's identity. That's Euler, not Euler. So, okay, let's first review a few powers of I, because this will be important. So I itself is the square root of -1. And then I squared is, so I take the square root of -1 and square it, so that just gives me -1. So I squared equals -1. And then for I cubed, so I can just really multiply the previous step by I. So that's really like I squared times I. Remember, I squared is -1, so -1 times I will just give me -I. So I cubed is -I. And then I to the fourth, well, I can break up I to the fourth as I squared times I squared. So that'll be -1 times -1, so that will just end up equaling 1. And then we cycle back, so I to the fifth gets us back to just I. So the first thing just to remember here is that powers of I cycle into I, -1, -I, 1, I. Okay? So we are talking about now Euler's identity, which involves e to the I theta. And so e to the I theta, we can actually relate that to a Taylor series. So specifically, here are some common Taylor series that you should know, ideally have memorized, and one of the really big ones to have memorized is e to the x. So e to the x is 1 plus x squared over 2 factorial, so on and so forth. Okay, so what you can do to relate this to Euler's identity is basically where you see an x, replace it with I theta. So all those x's are going to get replaced with an I theta. So I am just going to go ahead and expand that series. And what we want to do is we want to think about now what is actually happening with this. So I've got 1 I theta squared over 2 factorial, I theta cubed over 3 factorial. So if I just expand this, so look at what ends up happening. So I have 1 plus I theta plus I squared theta squared over 2 factorial, I cubed theta cubed over 3 factorial, so on and so forth. But remember, so I've got this I squared, I cubed, I to the fourth, I to the fifth. So you're right. So we have all these powers, and like we just said, so these powers just cycle from I, -1, -I, -I, 1, I, so on and so forth. So what I'm saying is all these powers that I've written out, I can use what I know about powers of I to rewrite this. So now I've got 1 plus I theta minus theta squared over 2 factorial minus I theta cubed over 3 factorial, so on and so forth. Okay, so for Euler's identity, the first thing that we notice now that we've simplified all these powers of I is that this particular series can be broken up into two different parts. We have the terms that have i's in them, and then we have the terms that have no i's in them. And so what we can do then is we can just rearrange these. So here are my terms with no i's, and they all end up being these even powers. And then I can factor I out of all the terms that have an I in them, and I get this set of terms here. Now, if you look at these two series closely for a moment, they might look very similar to other Taylor series that we've seen before. Specifically, they look very similar to sine of x and cosine of x, right? So sine of x was all of these odd powers, and cosine of x was all of these even powers. So what I'm saying is this series of even powers is really cosine of theta. That's the Taylor series, right? And this one here, this becomes I sine theta. Again, that's the Taylor series in disguise. So what does this actually mean then? What we have shown is that e to the I theta can be rewritten as cosine theta plus I sine theta. And this is what's known as Euler's identity. And so this is also kind of cool because then, surprisingly, you can simplify a lot of powers of e to the I whatever. So for instance, I could ask you to rewrite e to the I pi over 4. So if I wanted you to write that in, say, a plus bi form, which would be a complex number, what I can do is I can just apply then Euler's identity. So Euler's identity says that e to the I theta equals cosine theta plus I sine theta. Well, now I have e to the I pi over 4, So all those thetas will just get replaced with a pi over 4 like you see here. And then I can just evaluate what these are. So cosine of pi over 4 is 1 over square root of 2. And sine of pi over 4 is 1 over square root of 2. So this is I square root of 2, or sorry, 1 over square root of 2 plus I over square root of 2. And I can factor out that 1 over the square root of 2 times 1 plus I. So that would be putting this in a plus bi form. And so that brings us to the end of that one. So I'm going to leave it there, and I'll talk to you guys in another video. Bye!